Hello everybody, welcome to reactive intermediates carbene and nitrene. In our last class, we have discussed that how the carbenes can react and what are their reactions. As per example, we have started that different type of reactions. First is that addition reactions, so carbenes reactions rather, addition reactions. Number 2 is various insertion reaction, and finally we will learn different rearrangement. Okay. Now, in our last class we already started about these addition reactions. There what we have studied that when the carbene can add to the olefin, that can generate the cyclopropane. Okay. So, this method is very important and this is one of the most used method to prepare the cyclopropane ring. So, in general what you can make that the cyclopropane ring from the olefin. Okay. So, this is the additions reactions we have started to learn. Then we have understood from there that how the singlet carbene can react with the olefin. That means, if the singlet is the carbene is singlet, then how it react in concerted way, and if the carbene is triplet, then how it reacts in stepwise manner. Basically, we have understood the electronic nature of this carbene can be verified through these different experimental results. Apart from the spectroscopic method, we can measure the nature of these carbenes through these addition reactions. Through singlet, we can get only one product, but if it is triplet, then due to stepwise reaction, it will give more than one product. Okay. So, now today during the addition reaction, we will learn another very important reactions in this topic for the cyclopropane synthesis, that is called Simmons-Smith reactions. Okay. So, this is also another reactions where you can make the olefin into its cyclopropane ring mostly. Okay. So, unsaturated bond can be prepared to the corresponding 3-member ring. Okay. So, now what is this Simmons-Smith reaction, that we will learn. It was discovered in 1958. So, this is discovered in 1958 by two chemists, and these two chemists Professor Simmons and Smith. So, and this is one of the best method to prepare cyclopropane from alkene. Okay. So, now we will learn that what are the reagents that they use to do this reaction. So, what they have taken? They have taken this ICH2I, okay, that is methylene iodide, and in presence of zinc copper couple, that gives iodomethyl zinc iodide, okay, then it will be in equilibrium with it another zinc species plus zinc iodide. Okay. So, this is the iodo this is the iodomethyl zinc iodide, okay, and this is bis iodomethyl zinc. Okay. So, now this complex zinc complex will act as the active reagent. Though there is certain discussion and lot of investigations about this reagent has been carried out, and there are lot of different experiments were carried out with this to understand exact its structure. Though there are certain discussion about this are already in the literature, but this is the more acceptable way that people have represented this reagent. Okay. So, now this is we can think about that is like a zinc-carbenoid. We have already studied what is called carbenoid. Okay. So, you know already what is called carbenoid, you know that that also acts or that also behaves like a carbene, but it is associated with some other metals. Okay. Like here it is associated with zinc. So, now if we take one olefin, as per example here it is cyclohexene. So, in presence of Simmons-Smith reagent, that is the CH2I2 and zinc copper couple. Okay. So, this is called Simmons-Smith reagent. So, now if we use that one, okay. So, what we will get? We will get nicely from olefin to the corresponding cyclopropene. Okay. So, this is the basic fundamental reaction for the Simmons-Smith reaction, and this is called Simmons-Smith reagent. So, this is called Simmons-Smith reagent. Okay. Now, once this reaction is going, next question is that how this reaction is happening, what could be the probable mechanism, that we will learn. Let us see that how these reactions can proceed. So, we will take the starting material, that is the cyclohexene. Now, as we have already seen that this methylene iodide and zinc copper couple can generate this iodomethyl zinc iodide. So, that could be the active species for this reaction. So, we can write like this. Now, these reactions can happen in the concerted manner to give the desired cyclopropane ring. So, the transition state could be like this. Okay. Next, this is the 2 hydrogen that is over here. Okay. Now, this is the corresponding active species. Okay. So, this could be the probable transition state. So, this could be the transition state. Okay. So, through it these reactions can happen. Actually, this reaction is going via concerted way. Okay. So, I have written this transition state. Now, this can finally give the desired cyclopropane ring. Okay. So, this is the concerted way that can dictate up to this product. Okay. Now, this zinc-carbenoid actually here behaving like a singlet carbene. That is why this can react as a in a concerted manner. Okay. So, next we will what we will see, we will check some of the example for these Simmons-Smith reactions. We have seen that normal olefin how it can give the corresponding cyclopropane. Okay. Now, it is very interesting if there is some allylic alcohol, okay. This kind of allylic alcohol is there, then actually what happen in presence of this Simmons-Smith reagent, this reaction is giving only one diastereomer. Okay. So, this is highly stereospecific reaction. Okay. So, the overall diastereomeric X is that this diastereomer is more than 99% yield. Okay. So much selective reactions here. This is regioselective as well as this is highly this particular diastereomer is forming. Okay. So, now why this reaction is only giving this product? Okay. So, here actually the reason, probable reason behind this selectivity is the coordination between these heteroatom, here it is the let us say this oxygen is here. So, coordination between this zinc atom and this hydroxyl group in the transition state explain this faster this stereo selectivity. Okay. So, this hydroxyl group here or if it is some other heteroatom that can coordinate with this zinc-carbenoid and that dictates as here it is this particular one isomer. So, that actually dictates from which phase this cyclopropane ring will generate. Okay. So, here this coordination between this zinc atom and this hydroxyl group is very important. Okay. So, let us see how the probable transition state can be. So, if we see here that if this is our heteroatom, then actually these active species that can coordinate with this hydroxyl group and give this kind of transition state from which actually the cyclopropane can form from only one phase and give only this particular diastereomer. Okay. So, this diastereomer will be more than 99% this diastereomer. Okay. Okay. Another very interesting aspect of this reaction is that this reaction is much more faster, almost 100 times faster than its unfunctionalized precursor. So, if we think or if we compare between these two cyclopropanation of these two derivative okay, under similar condition, then actually what the experimental result says that the reactions of this alcohol, this allylic alcohol, this reaction is very faster. Okay. Reaction is very faster, very fast. Okay. Than its unfunctionalized precursor. Okay. So, what could be the reason? That again the reason is same, that due to presence of this hydroxyl group. So, it can easily coordinate with the reactive zinc-carbenoid, and that facilitates this reaction rate. Okay. So, this is the reason, that is why this reaction is almost 100 times faster than on normal cyclohexene. Okay. Interestingly, here I would like to mention that if we take any achiral olefin, okay, and we wanted to do its cyclopropanation using the Simmons-Smith reagent, in that case if we use as a menthol as a chiral alcohol, menthol is a alcohol which can be found as racemic as well as a its particular one enantiomer. So, if we take one particular enantiomer during the reactions with the Simmons-Smith reagent, then the product that we will get, the cyclopropane that we will get, that contains optical activity. Okay. So, this shows that during the reactions, when this active iodomethyl zinc iodide is forming, there this menthol is reacting with that and generating the chirality, so that it can give finally the optically active cyclopropane ring. Okay. So, this is another example where we can show that even though achiral alkene we are using, but that can give finally optically active alkene. Okay. Next we will see that another example, that okay. So, if we take this cyclopentene alcohol, okay. Now, if it is treated with the Simmons-Smith reagent, again in this case also this reaction is highly stereospecific. Okay. So, this will also give only one cyclopropane product. Okay. Okay. So, this starting material, this olefin also in presence of Simmons-Smith reagent will give this particular stereoisomer. Okay. Similarly, in another example, if we take this allylic alcohol again, okay. Here also you see very interesting, because in this case also under Simmons-Smith condition, the product that we will get again the heteroatom guided product, here the hydroxyl guided product, that is this one. You see here, even though this bulky methyl group is there in the ring junction, but still the cyclopropane ring is forming in that phase. Like here it is up bond, but here cyclopropane also forming with that particular stereoisomers, even that is not sterically inhibiting these formations, rather this hydroxyl group which is actually coordinating with this Simmons-Smith reagent or zinc-carbenoid, that actually guiding that in through which phase this cyclopropane ring is going to form. Okay. So, in this case, that is why this example is very interesting. Okay. Next we will see another interesting example, that is this one, where the olefin is highly substituted and it is again having some ester group here. Okay. If you see in ester group also, that is having some heteroatom, like here it is the oxygen. Okay. If you now treat with the under Simmons-Smith reagent, I am not okay. So, CH2I2 and zinc copper couple, what will be the product? If you take little excess of this Simmons-Smith reagent, then the product will be okay. Fine. So, in this case, this ester is directly affecting about the stereoselectivity of this cyclopropane ring. Okay. So, this is actually this ester group is guiding that in through which phase this cyclopropane ring is going to form. Okay. So, this is very interesting. So, that is why these highly substituted olefins became the cyclopropane ring through the corresponding ester guidance. Okay. But if we see that if there is nothing to guide, I mean there is no heteroatom or no such kind of guiding group is there, then what will be the consequence? Okay. Let us say you have this is the olefin, corresponding olefin, and if you have taken this olefin, okay, this carbene, then actually the product is that is generating okay. If you see here, these two cyclopropane ring actually trans, whether here these two cyclopropane ring, if you see, they are syn, but here they are trans, because here the guiding group is this ester group. This is the corresponding guiding group, or this is directing, okay, that from which phase this cyclopropane will form. Here as there is no such type of heteroatom or no such type of guiding group, that is why here these two cyclopropane ring that are trans to each other. Okay. Next, what we will see another example where we have the olefin as a exocyclic olefin like this. Okay. So, we have this exocyclic olefin. Now, little bit modified Simmons-Smith reagent, or little bit I can say that modified Simmons-Smith reaction, that they are in not here they have used the methylene iodide, rather they have used the methylene bromide as the corresponding reagent in presence of zinc copper couple. So, what that has given? That has given this product, that exocyclic double bond becomes the corresponding cyclopropane ring. Okay. Now, next what we will learn, that what will happen if these carbenes or this rather the Simmons-Smith reagent, if that adds to the corresponding allenes. So, addition to allenes. Okay. So, you know what is allenes? Okay. Allenes are something like this. I am not going to detail of its structure, how their orbital stays and all those things, but this is some kind of structure of allene. So, now there are also double bonds. So, if you take the carbenes or the Simmons-Smith reagent, how that is going to react with the allene. Okay. If we take one example, just I will show here as per example here. If we take this one, in presence of the Simmons-Smith reagent, okay, the product is you see here under the Simmons-Smith reagent only this double bond become cyclopropane, okay, this one. Why? Because again if you see this is near about one heteroatom is there, and that is guiding that in through which double bond is going to be cyclopropanated. Additionally, this is more substituted also this side. So, overall the product is this one, this cyclopropane ring with this exocyclic double bond. Finally, this one has been converted into a natural product, that is the hypoglycine A. I have shown previously also, this is a very important natural product. Okay. So, this is the corresponding racemic hypoglycine A. Okay. So, using this technique or using this reaction Simmons-Smith reaction, these allenes can be converted into the another cyclopropane derivative, which further leads to the natural product, that is racemic hypoglycine A. Thank you.